Good afternoon.
Good afternoon, sir.
Very nice. So looks like the interested folks are decreasing in number, or is it some urgent matter that they have to attend to beyond the class? Okay, folks. How are you all doing? How are you doing? No answer. You're doing fine. Okay, fantastic. Great, nice. Okay, so I have a decent number who listen to the class, discuss in the class. So I'm happy with the small number. Okay, so I can proceed now. Would you have any questions that you want to ask me? Aniruddha has a question.
No, sir.
No, sir. Please don't ask me that I have questions. All right. Okay. So, is it okay if I continue where I left off? Is it okay if I continue where I left off?
Yes, sir.
Okay. How about some of you open your camera? Sharat, Arpit, Ayush, Mohammed, Siraj, so that we can discuss better. It's a small number. It will be nice if you can do that. Denisha, Tara, go ahead. Just open your camera. Let's discuss today. Shall we? Can't hear you, yeah. So mum. I mean, is this the way that online classes go?
It's usually worse than this, sir.
Oh my God. Oh God. I pity, I don't know who, whether you or people who are on the other side. But either way, it is not very healthy, no? I'm hoping this doesn't continue. All right, okay. Yes, Siddharth, you had your camera on. Come on, come on, come on.
Oh, okay, sir.
Oh, okay, sir. All right. See, what I'm going to do is exactly the similar thing that we did for axial deformations, except it is torsion today. Okay. Okay. We're going to twist ourselves into torque and twisting. All right. Very simple ideas, just extracted, extended from axial deformations. Okay. So I have, this is where I left off. One good thing about blackboard in your office is nobody erases it except you, right? So I have this where there is a, let's say I'm going to call this as T1 and T2 acting on a bar, and it has two parts to it. One part has a diameter which is different from the other. Okay. The question, what could be the question that you will ask? Generate a question. Hey, why don't you folks just get your camera on here so that we can chat better. All of you, all of you. Azam, Saket, Janisha. Janisha has stopped her camera these days. What, Janisha? Oh, she's not there. Oh, she's there. Okay.
I'm here.
You're here. Okay. She heard it somewhere. Oh, she's here. Have your camera on so that I can talk better. Very difficult for me. I don't know if you are in this other side, you will understand what I'm saying. You agree, Janisha?
Yes.
Yeah, okay. At least you're sensitive. So, generate a question in relation to this. Quickly, Ayush.
Sir, what will be the effective?
Okay, one is, remember there are two torsional torques that were applied there. One is effective, okay. Effective, one is K effective. Huh? Okay, all right. Tara, quickly. Let's discuss. Else it will be boring to me, boring to you. Tara is not there. Okay. She opens it up and goes off. No. Tara, Aarti is it? Should I call you Aarti? No, no response. Arpit, are you there? Yeah,
Hello, sir.
Arpit. Oh, Tara is there. Tara, can you generate a question fast? Generate a question on this. Any question. Quickly, so that we can proceed and do something that meaningful today. All right, Megha, go ahead.
The twisting moment diagram.
Twisting moment diagram. Fantastic. So she wants to do find out twisting moment diagram. Okay. So twisting moment diagram. All right. Then twisting moment diagram. Anirudh, ask a question. Generate a question. Whenever we need to generate a question, it becomes difficult, huh?
Yes, sir.
Yeah. Just try it out.
I'm not getting anything to mind right now.
Oh, no, okay, no problem. Don't get nervous. Oh, what is the twisting? What is the angle of twist at B? Is that okay?
Yes, sir. Fine.
Okay. So alpha at B equals what? This is equal to what? Okay. Siddharth, again, your camera is off. Tell me, Siddharth. I'm just going by the tiles that are there. Siddharth, quickly. I know there is a ball that is in your hand. Siddharth. No, he has gone out and playing. Okay. Janisha. Generate a question. Generate a question. What's the point in just answering here? Ask questions. Ask question on this. Go ahead, Janisha. The mind is blank today. Okay, no problem. Sanket, you are there? Sanket? No response. Mohammed, are you there? Mohammed, this one?
Yes, sir.
Fantastic. Mohammed, can you ask a question in relation to this diagram?
Maximum twist at point C.
Maximum twist. Okay. Alpha max. Okay. Maximum twist. Okay. Where it occurs is immaterial right now.
Okay.
Very good. Good question. Then Ashwat, are you there?
Yes, sir.
Okay. Ask a question.
Sir, currently it isn't striking me, sir.
Why here? Am I looking like a I don't know, Rakshasa?
Not like, sir. No, sir. Like, whenever
Okay.
I study patiently, automatically something comes into my mind. Sir.
Okay. No problem. Each one has a particular way of interacting. Sriraj, ask a question. So remember, one thing, folks, this is the starting of asking questions. You ask questions, generate questions. Answers are very easy. You've been doing this over and over. Answers, yeah, Give me a problem, sir. I answer. Give me another problem, answer. Give me another problem, answer. Ask a question, no? Isn't that beautiful? Yes, Sriraj.
Asking problem itself a very big problem.
It seems to be a big problem. Okay, we'll solve that problem through asking, getting into the practice. Yes, Sriraj, I'm waiting.
And also, nothing comes in my mind.
Nothing comes to your mind. Oh God. Okay, Assam. Okay, I'm not going to ask Karthik. Vedant.
Sir, how about energy stored in
Sir,
the
I had
Fantastic.
put a
Who, is
question in
who
the-
asked that? Yeah, in the chat box. Okay. How about who asked that question? How about what?
Sir, me.
In the chat box. In the chat box.
Sir, I had posted a question in the chat box. I think you
Effective
didn't
twist.
notice.
Yeah, see, effective twist, Karthik, is a little bit vague. What do you mean by effective twist? At what point of the body are you talking about? Okay, that has to be clear. Okay. Yes, Azam. Sorry to interrupt, Azamuddin. Not there. Kinshuk.
Anirudh was giving some answers.
Anirudh. Oh, Anirudh, yes. Go ahead, Anirudh. No answers, questions only. Oh, you
Yes,
only
sir.
asked a question. Strain energy, huh?
Yes, sir.
You of what? You of
Alpha. Alpha.
huh? Alpha? Alpha?
I think alpha, like, or maybe theta, or I don't know.
Alpha is okay, but what is strain energy a function of? Strain energy, a function of
Strain.
strain.
Oh, okay, gamma.
Yeah, of course, no, that's why it's called strain energy. Azam, you wanted to say something? Karthik has to change his question. Kinshuk has just opened Zoom and gone off. Is that what it is?
Yes, I am.
Yeah, you're there. You're there. Yeah, ask a question. Ask a question. Let's see how many questions we can generate. Ask a question.
So
Anything.
last class you had given that formula of
This
how
right-
you got K
right-
effective.
Right now, ask the question.
Sir, am I audible?
Yes, Vedant. Ask the
Uh,
question.
Sir, last class you had written the formula for K effective. How did you get that?
That's what. See, we will come to that. Ask a question in relation to that. You assume yourself as a teacher and ask the question. How we did it, we'll come to. Ask. Okay. Kinshuk, go ahead.
I don't have any ideas.
Okay, Janisha, you're ready now.
No, sir, I had a doubt. Like, can we talk about determinate and indeterminate things here?
Oh, okay. So generate a question, no? That way.
So, is this a determinate structure?
Is this a determinate structure? Very good. Is this a determinate structure? Okay. Produce a question here. Kinshuk, okay. Who else? Aditya Ravi. Aditya Ravi.
Yes, sir. Yes,
Yeah,
sir.
go ahead, ask a question. Yeah. I'm interested in, questions that are tough to answer. Else
Why
they
is-
would have been boring for you, no? Yes, go ahead. Go ahead. Aditya.
What exactly is relation of alpha, sir? With the
What?
length.
What is the relation of alpha with the length? Are you talking about alpha B or alpha C? Is that alpha
Yes,
A?
sir. Yes, sir. Yes, sir.
Okay. Alpha A. Okay. Alpha A you want to find out. Alpha B you want to find out. Okay, fine.
Any point, sir. General
Like
relation.
Okay.
alpha as a function of the distance.
Ah,
Yes, sir.
fantastic. Alpha as a function of. So alpha as a function of Shall we just put x, x from here?
Yes.
Yes,
Is that
sir.
okay? X from here. Okay. Alpha of x is equal to. Fantastic. Okay. What is TMD then? It is, instead of this, what shall I ask? T of
Alpha.
x is equal to,
Okay.
yeah, that's TMD, right? Okay. Manavi, I have not seen you for a long time. No answer.
Yes,
Oh,
sir.
you are there. Okay. Tell me, Manavi. Question. See, one of the reporters asked me, news reporters asked me, so how do you generate exams? Right? We saw one of the question papers asking for questions. Then I thought, oh, okay. I told her that, our students are good in just asking as many questions as possible. Hope I'm right. Yes, Manavi?
Yes, sir.
Yeah, tell me one question. For example, if I constrain this, what would be the twist at B? You can ask such questions, no? Ask a question, that's all. Generate it in a very simple way.
Okay, so that way, sir, if we cut the system at point B, what will be the twisting moment at A and B?
Or if you cut the system fictitiously at
Point B, sir, in the middle.
point B in the middle. Like this, huh? All right. Okay. But who is asking that question? Who is
Siddharth,
asking?
sir. Siddharth.
Oh, okay. I'm not able to see Siddharth over
Yeah,
here.
wait, sir. I turn on video.
Yeah, okay. Manavi is here to ask. And then Dakshita. Manavi and then Dakshita, and then let's see how we can answer each of these questions. Go ahead, Manavi. Okay, you're generating the question in your mind. Okay, Dakshita. Hello, hi, Dakshita, are you there? Your Zoom is on. Your mic is not working. Chat is working. Very good. Ask a question on chat. But mic is not working. It's not a question. So ask a question. Joel. Harsh, are you doing okay? How come no answers here? Do you think if you stand this side and you're not responsive, the students are not responsive, can you proceed? That shouldn't happen. No, it's not fair. It's not fair. It's not fair. That's all I can say. All right. So let's just work out. Okay, one is twisting moment. Yes, Saket.
Sir, can we draw a graph between angle of twist and distance between the
Very good. Okay.
X?
Graph of
Angle of twist and distance between X, sir. X.
Is that what you're saying?
Yes, sir.
Okay, very good. Nice question. Nice question.
Sir, and also maximum shearing stress we can find.
What's maximum? Fantastic. Maximum. Tau, what is tau max? Beautiful questions you're asking now. Yeah, somebody else was Rishabh. Go ahead, Rishabh.
And see how will we incorporate that?
Not able to hear you properly, Rishabh.
Hello?
Yeah, little louder.
This is
Rishabh, are you talking? Yeah.
Yes, sir.
Go ahead. Yeah.
So, sir, I was asking, suppose there is a temperature gradient between A and C. How will we incorporate that?
Okay. What if let's make it simple now. What if temperature of the entire, is that okay?
Okay.
Body is raised. Okay. All right. Sriraj, what I want you to do, Sriraj, are you there?
Yes, I'm here.
Do you have a notebook? What is this here?
Yes, sir.
Okay. So please, folks, when you come to a class, there is a discipline. Discipline has nothing to do with properly dressing and all those. Discipline has to do with what the task would need. When you come to a class, there has to be something that where you note it down, points that occurred in your mind, right? Even if there is a video, what occurs in your mind is more important. Sriraj, you have a notebook and a pen?
Yes, sir.
I want you to just note down all these questions. And a few more questions are coming, right? Dakshita, Manvi, I'm not going to leave you. Karthik, you refined your question?
So we can ask if it is hollow or solid, or we can ask to find
Okay.
the depth.
What if, okay, very good question. See, only after I push you, you are asking question. What if, yeah, proceed further. What if this is
Hollow
AB and BC are hollow
or solid.
with a thickness, okay?
Hmm. Okay.
With a thickness T, or if it is
Solid.
solid, okay? Are you talking about same area, Manavi?
Yes, sir.
Yeah, same area of cross section, same CS area. Is that okay? Sriraj, you're writing down. Dakshita is pending. Dakshita is pending. Sanket could ask a question. Dakshita has asked a question, not yet. Effective twist, okay, one more circle. What angle of twist will remain in original position? The question is not very clear to me, but I think what you're asking is there a point at which it goes beyond elasticity? Is that what you're saying? Yeah, okay. So when does it, so failure, how does it fail? I'll just put it that way. All right. Okay, Karthik. Okay. So Sriraj has written all this. So let's answer each one of them quickly. Are you ready? Yeah. Number one. I'm erasing Sriraj. Is that okay? Say yes or no. Sriraj. Sriraj, you noted it down? Okay. I think Megha has noted it down. Yes, Megha? You noted down?
Sir,
I need to
have
erase. That's
noted
why.
it down. I have
The
noted
board is
it
very
down.
small. All right. Oh, fine. You have noted it down. So let's start with the first one of these questions, which is twisting moment diagram, right? Twisting moment diagram, right? Twisting moment diagram is very similar to, intentionally I'm going to change this to this direction, okay? Just to kindle your thought, okay? One is the T1 in this direction, T2 in this direction. What is T1 in this direction? I just have to use corkscrew rule or right and thumb rule, right? So which means that it is actually going in this direction. Okay. This means it is going in this direction. All right. I need to draw. Help me out, one of you, very quickly. Where should I start from? This side or this side?
To the right side.
How do I find out the twisting moment? What should I do, Anirudh?
So cut the part.
Fantastic. That's all. That's all I need. Cut is enough. All right. The moment you say cut, you understood what to do. Okay. I have to cut at a point which is away from the end, right? If I cut and draw the free body diagram, it's not very difficult for me. I should get the twisting moment, and the twisting moment will be in the opposite direction as
External
T1.
Oh, T1.
Correct.
Yes.
And therefore, I should do two things. One is, what should I do? There is something else missing when I have to draw a twisting moment. There's something else missing. What is that?
Coordinate axis.
Coordinate axis is one of them. Coordinate axis is one of them. All right. What's the other that is missing? I need to add over
Sign
here.
convention.
Sign convention. I need to say what is sign convention. Right? Sign convention, as we discussed earlier, it has to be like this. Right? In this case, it is like this. This is T1. Opposite direction is what should be T of X, correct? If X is within this, correct? Yeah? Is this positive or negative?
Negative, sir.
Negative. So let's draw that it is negative and it is equal to T1. So I'm going to draw that T1 over here. So far, okay? Let's look at BC. What do? I cut here. Quickly tell me what happens. What should I get? Let's say T2 is greater than T1, okay? In magnitude. Since I have not given values. T2 is greater than T1 in magnitude. Go ahead. Janisha, this should be simple for you.
Similar only, sir.
Similar line. So what should I get? What should I get as, is it constant in this BC? BC, is it constant?
Yes, sir.
Yes.
Yeah, and equal to
T2 minus T1.
T2 minus T1?
Or mod of T2 minus T1. Like, you have to see the sign.
Yeah, but you see, you have the sign over there. One is in this direction, the other is in this direction. You will get it to be T2 minus T1. All right. So I have drawn the twisting moment. Why should I draw twisting moment? Sir, the shear stress at each point will differ due to rod's weight. So won't that also affect twisting at different points? Yeah. So when you frame the question, you say, okay, the effect of self-weight is negligible right now. Okay. All right. But if you have to add, you can add that later again. I'll tell you how to do that. All right. But this is something that you do just for twisting alone. All right. Why am I drawing this twisting moment here? Anybody? What's the use of drawing this?
To find the amount of twist each position has.
Or in other words, these are the internal forces that affect twisting. And therefore, I need to draw this because this is very essential before I proceed to find out all the alpha, etc., etc. Right? What is alpha at this point? So let's draw that. Alpha of X is what the other one has said. Right? So this is TMD. The other is angle of twist diagram. Angle of twist diagram. Okay. Here it is. At this point C, it is. At point C, it is
0.
0. And then what will happen? It's a constant torsion that is applied.
Again, it will be constant.
I'll use flay, correct? As I increase X, I can use flay. FL by EA. Here it is TL by GJ, right? J I can find out, G I know, T is nothing but the twisting moment. L is the X that I get. It is varying as X. Fantastic. Right? So it is varying as x. Okay. At this point, it will be equal to T2 minus T1. Correct. All right. After that,
Starts decreasing.
it starts decreasing and it depends on this. So what will be at this point? Is it 0?
We can't tell, sir.
We can't tell. So there is something that I get. Okay. All right. So far, so good. From this, supposing I take this as axis, then it is nothing but T1. This is T1, right? So it is T1 L1 by GJ1. Okay. From this point, I need to subtract this in order to get this value. This is how I find out alpha of x. Sriraj or Mega, what is the next question? So we have answered alpha of x here, T of x here. What's the next question? Go ahead. Ask. Yeah. Fast, yeah. Come to speed. It also means that you have not been spending, just spend about half an hour just watching the video. That should be enough for you. Yeah, go ahead.
U of R.
U of alpha or U of gamma. Yeah. Now, who is going to help me out? The alert one. Who is the alert one here? Help me out. Why are you keeping quiet? Mega, you can do it. Help me out. Yeah, she's saying yes. The smile means yes. Okay. U of gamma. Right? What's the general formula? Integral. Do you remember? It has to be force quantity times the change in displacement quantity.
Yeah.
Change in stress quantity, which is nothing but stress terms are dotted with.
Sorry, sir.
Stress as a function of epsilon times d epsilon from 0 to epsilon. This is both these are like this, where the multiplication has to do with 1 to 1, 1 1 epsilon 1 1, sigma 2 2 epsilon 2 2, and so on. Right? That's how we wrote, and the half will appear automatically when I take out. All right. This is okay. If it is linear, it's easy for me to write down. If it becomes linear, what will I get here? If sigma is proportional to epsilon,
Can you move? Can you move your camera a bit?
If sigma is proportional to epsilon, it means that it is a linear elastic material that we are talking about. And we will get the usual formula that we know, which is half times
Sigma epsilon square.
Sigma epsilon, or half of E times epsilon square. This is what we got. So this is strain energy density. Strain energy density, because per volume is what we are talking about. Are you okay? This is what we did for axial. Because else I would get each term separately, right? Sigma 1 1 times epsilon 1 1 plus sigma 2 2 times epsilon 2 2, and so on. Here there is only one quantity, that's why I wrote this. So this is for axial. I need to now write for torsional, right? For torsional, what stresses are present?
Shear.
Only shear, right? Only shear. And therefore, what should I get here? Half
G.
Fantastic.
gamma square.
Yeah, very simple. Got it? That's as simple as that. This is what it is. Do I know gamma in terms of torsion, twisting moment? Yeah, I can substitute here.
Yes.
All right, so I can also write this in terms of twisting moment. I can write it in terms of alpha, because how is alpha related to gamma?
Gamma L equals R alpha.
Or in other words, alpha by L, which is alpha comma x, no? Alpha by L
Is gamma by R.
Gamma.
or R into alpha by L is equal to gamma, right? How does gamma vary with respect to central axis to the skin of the bar?
It increases linearly.
It increases linearly. Why?
Due to the
Gamma equals
alpha R by L.
alpha R by L. L is the same throughout. Alpha is same throughout.
R increases.
Which means that only R has to be now changing from the axis till that. All right, it is varying linearly. At the skin, it is the maximum. Somebody asked for maximum, so I'm just talking about that. Clear about it? All right. Now you can expand this and get it in terms of this. I want you to do that as an exercise for yourself. Okay. Now this is written in terms of what? In terms of gamma. All right. Gamma I can write in terms of T, right? So if I do that for just a bar with constant torsion throughout with uniform cross section, I'll get that to be equal to half T squared L divided by Gj. This is very similar. If you go back and look at axial, it was half F squared L by Gj. Okay. And it's also meaningful. I can write this as T times TL by Gj. And this is alpha, right? Half times T times alpha, right? Because if I draw T versus alpha,
Straight line.
will be?
Straight line.
It will be a straight line. And I can find out the area, right? And that is half times T times alpha, right? Is this clear? So this is what I have. I can do one more thing, which is hyperelasticity. What is that? U of total divided by dou alpha, you can take it as T, okay? Dou T should be equal to
Alpha.
Can I do this? Dou U total by dou T? The answer is no. If this is a strain energy, it has to be dependent on a displacement like quantity. Okay. But you will figure out later that U total is also equal to U bar total. Okay. Just as I showed you in the diagram, whether I take this area or this area, it's exactly the same, and therefore they match for linear elastic. So for okay, so I can do this, and this will give me alpha. If I do this, I should get the twisting moment. Correct? Hyperelastic formulation. This is very useful because what I can do here is somebody asked me a question. What was that question? Oh, tell me, sir, what would be the twisting occurring here? What will be the twisting occurring here? What will be the twisting occurring here, etc., etc. You remember when you go back to what we did for axial deformation, whenever we wanted to find out the displacement, what did we do? We applied, you remember, you applied a load, found out the deflection, and put that load as equal to 0, and you got it. Do you remember that? It's exactly the same thing I can do here. This total could be for the structure itself. And I do the same thing. That's the beauty of using hyperelastic formulation. So far, okay? I know I'm rushing, but I'm rushing because we have dealt with axial deformation, stretched it enough amount of time. Right? So this will not be twisting you too much. This will not be twisting your brain too much. Yes, Janisha? All right. What's the next question? Megha, Sriraj. Ask the next question, no?
Alpha is a function of x.
We already did. It's here.
Yeah.
There were some nice questions that were
Graph of
asked.
alpha of
Come again?
graph of alpha of x.
This is the graph.
Okay.
Yeah.
Uh,
This is the graph here. This is alpha of x. Any other question that was asked? K effective, huh? K effective. Okay, K effective of this, if I'm looking at this end, that's very simple, no? Can anybody tell me what it is? I can find out K1 of this. I can find out K2 of this. What is K1? Quickly, K1, K1. Oops. K1. Go ahead, go ahead. K1. Always remember axial deformation. It's easy for you.
GJ by L1.
GJ by L1. GJ1 by L1. K2 is GJ2 by L2. K effective, which is at the end that we are looking at, is this is in what? Series or parallel? Series. So what should I get?
1 upon K1 plus 1 upon K2.
That's it, over. Right? All right. Next question. Megha, Sriraj, go ahead. Next question. Next question.
next question will be, what if AB cross AB and BC are hollow with thickness?
Hello. Okay. Hello. Coming now. Okay. All right. So we have this, right? Let's say this is solid. We said at this extreme, the maximum stress occurs. At this point, it is equal to 0, right? And this is tau max. This is 0, and it is linearly varying like this as R. Right? This is what we figured out. Tau max is equal to T R by, this is R. Tau max, tau is equal to T R by J, right? T and J don't vary. As I change the R, it varies as R. Okay, and therefore maximum is over here. Supposing I take this portion off and draw like this, does the maximum change? As long as J is retained, it doesn't change. All right. Now, so if you ask that question, okay, for the same J, if I have to find out tau max, nothing changes over here, and therefore tau max remains the same. But if the radius, the total radius, this R remains the same, I keep that R and ask you the question. The cross-sectional area remains the same for both the solid and the hollow, and tell me what happens. Okay, and that's a simple question. Now, with respect to radius, that is, let's say if I take like this, as long as I'm inside the hollow, the stresses are zero. I know it. As I go into the bulk material, it's going to be varying like this. Correct? Yeah. Listen to me carefully. Now, I'm saying don't change the total radius, but you can make it hollow with the same cross-section area. Okay, so area remains the same. Radius remains the same. The total radius remains the same. Tell me which is the best. Is it solid or hollow? That's the question. If you ask, the answer will be solid will be better. Why? J will be larger for solid, and therefore tau max will be lesser. So solid is better when it comes to that. But if I ask, change the question a little bit. Instead of, I'm sorry, did I make a mistake here? Did I make a mistake? If I say bulk of, yeah, I have made a mistake.
Yes.
Yes. If I don't change the radius, this total area may remain the same, but the bulk of the solid would have changed, right? So I want to rephrase the question. Anyone who can help me out with rephrasing a question? Let us say I have the area of cross section given to me. Okay. Initially, it is a cross section which has radius r. Okay. I want to take this material and now make a hollow tube out of that. Okay. I can't increase the amount of material. I just have to use the same material. I just have to use the same material. Okay. Which means A remains the same, right? I need to find out J, right? T does not change. T does not change. Are you with me so far? T does not change. Area times radius of gyration. So shall I put it as RG? Radius of gyration square is J. Okay. Area remains the same. I need to now figure out how much I can increase J so that the stress comes down. So that that bar is more effective in taking the torque. So I repeat this once more. As I decrease the stress, it is good for me, correct? Right? Which means I should increase J. If I have to increase J retaining the area, I need to increase the radius of gyration. Give me a clue as to how I can do that. Naturally, if I have an area which is in between like this, the radius of gyration for this is only this much. I want to increase it, maximize the radius of gyration. The only way that is possible is I put all the material at the periphery. Correct? So that this is the RG that will give me a good J. Okay. What would be this value of RG? It can be infinity also. Why? Because the thickness can keep on changing. Right? As I decrease thickness, I can go for a larger RG. Okay. So if I put a limitation saying that you cannot go beyond a particular thickness, I limit the thickness saying, okay, don't go below 1 mm. Then I have an answer. This hollow rod or tube is better than a solid torsional bar, solid shaft. Is this clear? Yeah. So what am I looking at? I'm looking at J. Okay. We looked at R in order to find out what would be the change. Here RG also will keep changing, which means that this R also may go up. You have to watch out for that. So I should now write it as T by J by R, and Instead of maximizing this, I want to maximize J by R. Okay, are you with me? Just a minute of focus. J by R. We call this as section modulus. For example, what is J for a solid cross section? 2 pi R for J for a solid cross section, pi R J, moment of inertia for a solid cross section.
Pi r cube.
Pi R cube, pi R, pi R, pi R. Yes,
Yes, sir.
right? So J by R happens to be pi R Q by 2, correct? If I have a hollow one, what would it be? This is for solid. J by R, J by R for hollow. Hollow. How will it be? 2 pi R T, 2 pi R square T. Help me out. 2 pi R T is the area. 2 pi R T is the area times R square. Correct?
Yes, sir.
Which is R cube divided by
R.
R. Which means it is 2 pi R square T. Okay. Now pi is common here. You can take the ratio here and find out which one has to be appropriately modified. Got it clear?
Yes, sir.
This exercise is what is called design for you. Okay, where you want to maximize the advantage and minimize the damage. Okay, that brings me to the last point, which is damage. Okay, for the axial deformation, what did we do? We pulled a piece of chalk and it broke into two pieces with a vertical cross section. Correct? We had something like this. I pulled a piece of chalk, and it broke like this, right, into two pieces like this. Why? Why did it happen? Because the principal stress, sigma, is in this direction, right? And when sigma goes to sigma max, failure occurred. Correct? Now, if I do the same thing, twisting on this piece of chalk, what would happen? I take this piece of chalk, I now twist it and break it. It obeys this kind of law. What should happen? Quickly.
So it will damage and break.
It will break, okay, but what kind of breakage will you see? It's a shear stress. If I look at whatever I've drawn here, it is a shear stress.
Yes, sir.
You did more circle and all those. You did an assignment also. There is only shear stress that is available, which means what? How does it look like? 0, tau,
0,
tau, 0,
tau and
right?
tau and 0.
Right? Pure shear condition. For a pure shear condition, what should I find out? What is sigma here?
Sigma y by
is
2,
the
sir.
sigma.
Y by 2, sir.
Don't say y.
Yielding stress.
Yeah, but what should I find out? This is the stress I know. What should I find out from more circle?
Principal
I should
stress.
find out principal stress and then equate it to sigma x. And what is the angle of principal stress?
0 and 180.
Hey, listen. This is along what direction? X and Y, right? Along what direction is the principal stress?
X
2 theta is equal to
180 and 0. Like two values also, like here.
Come on, yeah. More circle. If I have to draw this,
45.
it is like this. It is
45.
45. So if a piece of chalk has to break by twisting, what will you notice?
Oh,
How
it'll
will
break
it break it?
It'll break in the plane of 45 degrees inclination.
Exactly. Fantastic. Look at this. Can you see? You can even measure and find out, oh, okay, is it obeying the brittle material law? Okay. As simple as that. I need to find out, I need to appropriately use. Whereas if it is a ductile material, it will fail appropriately in that. By the way, one more last thing before we leave, which is this. Gamma X, Y, we know, right? When we had something like this and this is X direction, gamma XY we know. That's what we have been dealing with. What is gamma YX? Or tau? Let's look at tau then. Tau or gamma doesn't matter. On the Y plane,
in X direction.
right? So we are looking at a plane whose normal is in Y direction. Tau XY is something like this, correct? This is exactly the same as the tau XY that you see on the face, correct? Yeah. What does this mean? It means this. Just notice this carefully. Are you able to see this? Yeah. Yes. I'm not going to twist and observe what happens. You can see it. I'm twisting now. You can see what happens. Twisting the other way. What did you see?
So there is also an axial deformation.
Yeah, it's very simple. All I have to do is, if I have a sheet of paper, just roll the sheet of paper. Do it by yourself. All right. Roll the sheet of paper and twist it, and notice what happens. What happens? What happens? There is a movement in the axial direction, right? But if I glue it together, for example, in this, I'm using a sellotape here and putting the sellotape over it. Okay, I put the sellotape now. Okay, what should happen if I twist it now?
No axial deformation.
It is resisting that movement. What is the resistance to movement called?
Inertia.
Force here. That's why you have constraints. Whenever there is a constraint, there is a force, no reaction, right? So what is that force? That's a shear force along this direction. As simple as that. Clear? Do you understand this? Okay. I've exceeded time. Sorry, I have a you have a 2 o'clock class, I know. Sorry, I've exceeded time. You go ahead. Thank you for attending today's class. There is a problem with Monday's class, but I'll let you know by WhatsApp. Okay. The next tutorial will be ready. Please be on it. I see most of you lagging behind, which may not help in this month, the coming month, because we're going to deal with torsion and bending. Unless we are able to intuitively understand this, it's going to be tough. All right, folks. Dynamic, yeah, Siddharth, I'll do dynamic later, but you have to teach us dynamic on Monday's class. How about that? All right, folks, enjoy. meet you on Monday or Tuesday. I'll tell you.
Thank you, sir.
Thank you,
Bye.
sir.
Enjoy.
Thank you, sir.
You have the JEE advanced exam happening this Sunday, right? I'm sure some of you must be helping your friends.